All right, this is 11.3. This is on the dot product. So we've seen with vectors that there are a few things that we can do. Like you can add vectors, subtract vectors. Let me give a little intro here. So given vectors A and B, we can do things like A plus B and A minus B. And we can do something like CA where A is a constant. Or where C rather is a constant. But if you notice that we haven't said anything about multiplying vectors. So the question is, can we multiply vectors? So in mathematics, really, you can do anything you want. The question is it useful? In other words, the better question is, can we multiply vectors, ... let's say, in a useful way? That's the important thing. If it's not useful, then there's no reason. So the answer is yes. Primarily, there are two ways, or at least there are two ways that we'll look at. So the two ways we'll study / use. And so the first of these is the dot product. And then 11.4 will be the cross product. So this is what we'll do. So we'll say given two vectors, we'll have, say, A is A1I plus A2J plus A3K. Those are just the components. B will be B1I plus B2J plus B3K. We'll define the dot product. This is also known as the scalar product. Either of those terms is fine. So the notation for this is A dot B. This is like a serious dot, not like a small dot, which can look like multiplication. So this is a lot more, has more emphasis. So what I'm going to do is I'm going to multiply the corresponding coefficients. So A1 times B1. But I'm not creating a vector. I'm going to create a scalar, hence the term scalar product. So keep in mind this guy right here. Let me emphasize this. This is a scalar. In other words, it's not a vector. Now, let me give you an example. For right now, don't worry about why this thing is useful. Just notice that it gives a result. So if I have like 2I plus 3J minus 4K, and say 0I minus 5J plus 3K, and if we dot them, we get 2 times 0 plus 3 times -5 plus -4 times 3. This will be -15 minus 12, which is -27. And again, don't worry about what this number means. Right? It's not at all clear yet. Just notice the calculation works. And just a little note here is in 2D, this is fine too. There's just no K. There's no K's in the vectors. So in other words, you just, A1, B1 plus A2, B2, and that's it. So this is the definition of the cross product, of the dot product rather. So what I want to do next is I want to talk about the basic properties of this thing. In other words, like what does it do that's useful to us? So I'm going to divide this into two sections. Let me call these actually basic properties and perpendicular properties. So the basic properties, these are pretty easy to remember. So we'll say the dot product obeys the following. So you might wonder why it's called a dot product, right? Sure, there's some multiplication going on in it, there's some addition going on in it, but it's called a dot product, emphasis on the word product, because it behaves like a product, right, in the following sense. So when I write these down, think about multiplication that you know, right? So in other words, if I do A dot B, I get the same as B. That's a terrible equal sign. That's the lousiest equal sign. We get the same as B dot A. That's like regular multiplication, right? For example, if you do 3 times 5, it's the same as 5 times 3. So second rule is distribution. So if I take a vector A and I dot it with, say, B plus or minus C, right, I can distribute the multiplication over the addition or subtraction. All right, so just like 3 times x plus y is the same as 3 times x plus 3 times y. Like that distribution works. So it behaves like a product there. And lastly, I have associativities. In other words, if I have a vector A and I multiply it by a constant, notice the C here is a constant. If I take that and I dot it with B, that's the same as doing A dot CB. In other words, it doesn't matter where the constant goes, which is the same as putting A in front. So again, just like if you have 3 times x times y is the same as 3 times x times y, or x times 3 times y, and so on. So it doesn't matter where that constant goes. So when you look at these, they shouldn't surprise you. They may not be obvious, right? Like you may have to sort of work through the calculations to see that they're true, but I don't want to worry about those details. You could just sort of look at them and be like, okay, obeys the properties of a product. So that's good. Those are the basic properties. So what I want to look at next are what are called the perpendicular properties. And those are the ones that we'll use in a more application sense. So let me clear this screen off and do those. Because then we'll call these the perpendicular properties. This is possibly not the best name, maybe angle properties or something like that might be better. That's right. So this is what we have. And so everything basically stems from A. So A says the following. It says, given, I'm going to turn this into a little discussion here, given vectors A and B, if we anchor them at the same point, there's an angle between them. So for example, just visually, if I have, say, A right here and B right here, then there's an angle formed between those right here. So theta, let's call that. So it turns out there's a relationship. This is sort of really the useful part about the dot product, is that what this relationship gives us. It turns out that if you take A and dotted with B, that dot product is actually equal to the product of the magnitudes times the cosine of the angle between them. Now, 2 notes about this. I'm not going to prove this. This is proved using the law of cosines. If you've forgotten that from pre-calc, that's fine. You can look this up in the book if you want. It's not particularly long. It's just a bit icky. So I'll omit this. The other thing to keep in mind is that this is actually sometimes used, this happens in physics a bit, is this can be used as a definition of the dot product. So instead of defining it the way that we defined it, you can define it this way. The only reason I mention this is, you may look in physics books, you may look in engineering books, you may look in other books, and you may see the dot product defined this way, and you may be confused because you may say, well, we learned it as a property, but that's okay, it doesn't matter. Right? So here's the important thing that comes out of this, or a couple important things, but here's the first big one, is that think about what would happen if these angles were perpendicular, right? If if the vectors were perpendicular. If A and B were perpendicular, the angle would be 90 degrees, pi over 2. The cosine of 90 degrees is 0, and the dot product would be 0. So therefore, it turns out that the dot product is 0 if and only if this is, let me write equals 0 here. If and only if A and B are perpendicular. So this is one of these things in the course that will come up repeatedly, right? Like all over the place. It will become second nature to you. Like I would say memorize it, but you'll use it so frequently that you don't need to memorize it. You'll memorize it automatically. So for example, if I said to you, say A equals 2I minus 3J, and B equals 1I plus 6J perpendicular. And all you do is you go, well, take the dot product. You get 2 times 1 plus 3 times, negative 3 times 6. You don't get 0. So no. All right, that's it. So really nice, simple test of perpendicularity. And then the other thing that comes from this is that if you have a given vector, right, you could say we have, if you look what happens when you dot a vector with itself. There are two ways to see this, but it falls nicely out of this cosine rule. Right? This becomes the product of the magnitude of A times the magnitude of A times the cosine of the angle between them. But if they're the same vector, the cosine is 0. Right? It's a 0, not a theta. So that's just the magnitude of A squared, because the cosine of 0 is 1. And also follows from this that the magnitude of A is the square root of the dot product with itself. These are small things that we won't use so much. Let me sort of make a little comment here in terms of priorities. Like B is the most important thing. I'll give that like 3 exclamation marks. Right, really, really you'll use this a lot. A, everything follows from A. A is sort of second most important. Again, you'll use it enough that you won't really think overly much about it. And C, we won't use much, but keep it in mind. So these are the perpendicular properties, right? So there's one last thing that follows from the dot product. It actually follows from these perpendicular products and the cosines and stuff, and that has to do with vector projection. So let me clear the screen, look at vector projection. I'm going to derive the formula for that, give an example. The idea of vector projection is something we'll use a lot later on in the course. So 5. So I want to begin this by sort of giving a visual example. So consider this situation. Let's say the vectors A and B shown here. Let me do these in blue. This will be B. I'm going to anchor them at the same point. This is A. So if you think of these, for example, as forces, you might look at this and you might ask yourself, for example, like, well, A is not parallel to B, it's not perpendicular, but like there's a part of A that goes in B's direction, right? So I'll write that and then I'll draw a picture which will really nail down what we're saying here. Right? We can say there is a, quote, part of A which goes in the direction of B. So I'll draw a picture for that so you'll see what I mean. So here's B again. Here's A. And so what I'll do is, if you imagine dropping this down perpendicularly and creating a new vector right here. So this is like it's like the part of A that's in B's direction. This is what we're interested in. Now, what is this vector? So the definition of this, or the notation, if you like both, is this is the projection of A onto B. So the order of those matters, right? So if you think about the words, it's I'm projecting A onto B, which if you look at the picture, that makes sense. This is the projection of A onto B. This is denoted. There are a few ways you can write this. The book writes this out really longhand like this. So notice the B is a subscript. It's lower down, and this is a useful way to remember it because it's lower down, so sort of A is above it, it's on top of it, so A is getting projected onto B. Right? Or if you want to be a bit lazy, you could just write PR. Or some textbooks will use like a capital letter pi. I would possibly suggest not doing that because it's also, capital letter pi is used for other things as well as mathematics. So I would use one of the first two. So this quantity is used when we're dealing with forces. For example, if we want to say like, well, how much of, if A is a force, how much of that force is in B's direction? Right, so in other words, if A is a force, how much is in the direction of B? Right, this is like a use of it, right? So what we need to do is figure out a formula for this, right? Like if you know vectors A and B, how do you come up with a formula for the projection? We'll be using this formula later on when we start analyzing behavior of forces, behavior of fluids, things like that later in the course, especially in chapter 15 at the very end. So let's work it out, right? Let's actually just work it out. So let me go back, draw the picture again. We're going to do this very, very easily. There's our B, there's our A. So the first thing I'm going to do is I'm going to figure out how long this vector is. Right? So I'm going to draw this line down, and I'm going to ask this question, what is the length of this? So this isn't hard to work out. Let's fill in some details here on this picture. Right, there's a little triangle going on here. The length up here is the length of A. There's an angle in here. And let's call this length L for the sake of argument. For now, right? So if you look at that right triangle, you automatically, right, it's a right triangle because of this angle, you automatically think of cosine because the cosine is the adjacent over the hypotenuse, right? So we have, let's go back to, let's say we have the cosine of theta is the adjacent, which is the L over the hypotenuse. So this tells us that the length of this guy is the magnitude of A times the cosine of theta. That's great. Okay, fantastic. Then the question is, okay, so it's length L, but what's the actual vector? Right? So let's think about what it is. It's a vector of length L, which goes in the direction of B. So what we'll do is this. We'll take B, we'll shorten it so it has length 1. We can do that. We saw that in 11.2. And then what we'll do, we'll lengthen it again to make it length L. All right, so this is what we'll do. Let's build it up, right? So I'm going to start in the middle of the page here. I'm going to take B. I make it length 1 by dividing by its magnitude. Remember, this is now the unit vector in the direction of B. Right? This has a length of 1. And then what I do is I make it the correct length by multiplying it by L. So just to really emphasize this, this is length 1. And this guy is length equals L equals desired. All right, so this is a vector that has the desired length in the desired direction. So let's just simplify this a bit. Let me clear off the left-hand side of the screen. I don't want to erase the whole screen, but the left-hand side isn't needed because we have the right-hand picture. So let's clear this up a bit. Let's tidy it up. Because this isn't really a great formula. Like, it's a perfectly good formula, but it's not great because it has a cosine in it. But remember the following. Right, we know the magnitude of, oh, sorry, let me do this right way around. We know that the dot product of A and B is the magnitude of the products times the cosine of the angle between them. So that says that the magnitude of A times the cosine of theta is A dot B over the magnitude of B. That's just dividing both sides by the magnitude of B. So I'm going to take this, plug it into our formula, right? This formula right there. So here's the result. Is that the projection of A onto B. Right? So taking the formula from the right, the magnitude of A times the cosine of B, that is A dot B over the magnitude of B times that big parenthetical thing. So this can be tidied up. So keep in mind, out of all of these things, everything's a scalar except for the B vector. Like the dot product gives us a scalar, the magnitude of B is a scalar. So when all this is tidied up, this is what we get. Typically written this way, right? Now, I'm going to put a box around this, and I'm going to also write it a slightly different way. So AKA, so we also saw previously that the magnitude of B squared is the same as B dot B. So this can be written this way as well. The book tends to use the first one, I tend to use the second one. I don't care which one you use, doesn't make a difference. So let me just do an example. I'm going to do an example just so that you see how to do it, to work through it, so that you see why we're arranging the symbols the way we are in the formula, and just to really sort of drive it home. So let me leave the left-hand side, clear the right-hand side, just work through it. I'll do a simple two-dimensional example because then we can plot everything and see what's going on. So here's an example worked out. Let's do A is something like, let me think about it. I want to do one that has a reasonably nice picture. So we'll do B is say 1I plus 7J, and A will be say 3I plus 2J. So let's find the projection onto B of A. And then we'll plot them both, and so that we can see. The formula says that the projection onto B, I'm flipping between notations. Sometimes I'm writing PR and sometimes writing PROJ, no big deal. This is A dot B over b dot b. Again, you can write it the first way if you like, doesn't matter, times b. So let's work this out. So let's write every gory detail here. So a dot b is 3 times 1 plus 2 times 7. B dot b is b dotted with itself, 1 times 1 plus 7 times 7. This is all multiplied by the vector b. All right, so the reason for writing it this way is so that the thing in front is a scalar. The big fraction is just a scalar, and then the other part is the vector. Let's tidy this up. This is 14 plus 3, which is 17 50ths. This is 17 50th. I is plus 119 over 50j. So here's a picture. And this doesn't need to be perfect, but I want it to sort of be good enough that we look at it and we believe that it's true. In other words, I want to have a pretty respectable scale on it. So let's do A and B in blue. So A is 3 units over, 2 units up. I'm going to anchor these at the origin. They don't have to be as long as you anchor them at the same place, but anchoring at the origin makes sense because everything is sort of nice and consistent. So A is 3 units over, 2 units up. So A is like right there. B is 1 unit over, 7 units up. That's really, really long and vertical. That's B. Now, what I'll do is I'll draw the projection without worrying about the calculation we did. So if I project this perpendicularly, this is the result that we get. That's the projection right there. Now, if you look at the calculation that we did, right, 17 over 50 is 34 over 100. That's 0.34. 119 over 50. This is 238 over 100, or 2.38j. We don't need to rewrite these in decimals, but this gives us a feeling for how long this vector is, like what its values are. So this is about 1/3 of a unit over and about 2.38 units up, and that's about right. My picture's not perfect, but looks good. It makes sense, right? I mean, barring not the best picture in the world. So that's an example of vector projection. And the final note that I want to make, which I'll just jam in the middle here, is don't lose track of the fact that the A's and B's are just positions. So if I project B onto A, this is different than the projection of A onto B. Right? And in fact, the projection of B onto A, you just flip the letters around, right? So it becomes B dot A, which is the same as A dot B, over A dot A. Oops, that's an A down there, times A. So think of the A and B as variables. Like, don't get too strung up in thinking about what's what. Just sort of think of them as variables. So whatever happens to go in there happens to go in there. But the projections are different, right? If you project A onto B versus B onto A, you'll get different results. So that's the end of the dot product section. We'll call that done.